Hello friends, welcome to this tutorial of AI and machine learning, and today we will discuss about the time series data analysis. So what is a time series data, and then how you can analyze and decompose the various component of the time series data, and then how can you do the future forecasting using any statistical method. The most popular one, the ARIMA model, what we will be using in this series or in this tutorial. And then, like, what are the various factors you need to do in data transformation to be fit for the statistical model to apply. And then what are the orders you need to concentrate before applying the ARIMA model. So let's start. This will be a very, important section of this series, and this will be very attractive and fun one. Let's begin. So first thing, what is a time series data? So a time series data is a data where the data is taken at some specific interval, like daily rainfall, hourly temperature, weekly heart rate or the blood pressure, or yearly, total number of sandstorm or any kind of tornado or T-storm coming towards your city. So these are all the data which is taken at some interval. Interval means hourly, daily, weekly, or yearly. Any interval is fine, but if it is taken at some interval, then it's a time series data. Now there can be two types of time series data. The variable which is most significant, and you want to forecast it like for the future, like if the rainfall is 100 millimeter today, what will be the rainfall in the next year today? Okay, so that is the the specific variable you are talking about. So that is called univariate. Okay, so and for all time series data where you can use the future forecasting, or you need to do the future forecasting, there this univariate data is used, not any other multivariate data. Okay, so now let's see how you can do the time series data analysis. So let's begin with some use cases. So like it can be used for the business future forecasting, like what could be the sales in my next 5 years, or it can be done for the history and present as well, like understand the past behavior of any symptom or characteristic, or evaluate the current accomplishment as well. Okay, but we will be concentrating on the future forecasting using the univariate time series data model. Now, what are the cases where you should not use the time series data analysis, or there is no need to do the time series data analysis? So let me draw a graph here. So this is my graph, and see, this is the time, and this is the variable. Let's see, x. Okay, now please excuse me, I am doing this kind of drawing using the mouse only, so maybe my handwriting will be very hard to understand, plus please bear with me. It's just for ease of your understanding. So let's resume. Okay, so if this variable is like constant for any time interval, so like at t is equal to 0, or t is equal to 1, or t is equal to 2, the x value is constant, then you don't need to do any time series analysis, right? It's obvious what would be the X value in like any future date as well. So another way is like there is a mathematical function to establish the relationship between t and x. Okay, like it's a sine curve, okay, or it's a logarithmic curve. Okay, so then the function itself can give you what could be the value of that data in some future t point, right? So then also you don't need to do any kind of time series analysis. Now, where I need to do the time series analysis, okay? So then the complexity of the time series data is given by like 4 components of it. One is the trained component. That means let's draw it again. So this is your variable and this is your time. Okay, and now if your variable is the mean of it, okay, so if this is the mean of these all data points where from I draw these curves, so if this mean is increasing or decreasing over time, then you need to do, this is called the trend. Okay, and then the second part, like the seasonal variance. What is seasonal variance? Like ice cream sale increases in summer. Okay, so if this point is summer, then ice cream sale will increase at this point. Okay, and then there is a, like a down point where like you can say this is a winter where ice cream sale decrease. Okay, so this is called the seasonality of in your data. Okay, and the third part is just a noise or irregularity. Like I don't know, like there is nothing which can explain some behavior of the data. Like, you know, if this curve has just a hiccup here, okay, I don't know where this hiccup created. Okay, so this is called the noise or irregularity in your data. Okay, and the last part is the cyclicity. So if any like behavior happening for a large period of time, okay, so you have taken the data for, you know, you say it like it's 10 years. Okay, and then in every 2 years or every 3 years there is a, you know, uh, increase in the cells, but this is called cyclicity. Okay, so and like some more example of the cyclicity, like some comet may visit near earth in like 60 to 80 years. Okay, some maybe in millions of years. Okay, so these are called the cyclicity, but mostly we will concentrate on the decomposition of the 3 parts E, T, S. E means the error part or the irregularity part, T means the trend part, and S means the seasonality part. And we make the data stationary enough to be fit for any statistical model to apply. Okay, so this will be the decomposition of E, T, and S. Okay. Now, what is stationarity? Okay. So, again, I need to draw this plot. Okay. So, this is your T and this is your variable. Okay, so this is your variable and this is your T. Okay, now if this seasonal and trend and these kind of random components, these three things are so high, then the variance like this mean, so this should go between them. So but bear with me. So if this mean and the standard deviation is going like varying very highly over time, then you are not removing your ETS components. Okay, then what should be your goal? You should have this line like this. Okay, so let's draw this again. Okay, so all the data points can be like this. Okay, or it can be at 0 as well. Okay, so then what is happening? Your mean is constant, and then if there is like, this is what, this is like you are removing your trend component. Okay, and you just removed your error data or irregular data because that's not contributing anywhere, you cannot predict it. So let's keep it out of the calculation. Okay, so by making the standard deviation, by making the mean constant, you are actually making the trend part removed, and by first initially you need to remove the noise part as well to take it completely out of picture of this calculation. The next part is making the standard deviation also constant or 0. Okay, so there actually what you are doing, you are removing the seasonality as well. Okay, so the variance is very low. Okay, so it is like this. Then this, when you see this kind of plot in your time series data after the data transformation, obviously, then you can say that this is the ideal data to be fit enough to apply any statistical model like ARIMA. Okay, so this is where you can achieve the stationarity. Now this is a visual method. Okay, so like there are two way, like there could be like multiple way, but we'll discuss about one visual way and another that calculative way to get how much stationary is your time series data. Okay, so then only if you get these two things achieved, then only you can proceed for the further statistical analysis. Okay, so let's start with test to check the time series stationarity. First is the rolling mean and rolling standard deviation. What is rolling mean and rolling standard deviation? Right, just an example, you have seen like the COVID-19 data. So it is like it can give you the daily data, or you can take the average of last 5 days as today's data. Okay, so like if I have like 1, 2, 3, 4, 5 in my last 5 days, so what will be my today's rolling mean? That will be 3 only. Okay, and then what would be the next one, like 2, 3, 4, 5, 6. Okay, so what will be the rolling mean? Like this will be 4, right? And then like this will be 3, 4, 5, 6, 7, and then that will be 5 only. Okay, so this is how your rolling like average or rolling mean is calculated. Okay, the same way apply for the rolling standard deviation. So now if you have this rolling mean and rolling standard deviation, okay, then like you can get, if this is like, you know, near to zero, both these curve, the orange one and thus this green one, both these curves are near zero like this, okay, then by visually inspecting that plot, you can say that your time series data is stationary enough. So that is the one way of testing it. Okay, take the rolling mean, take the rolling standard deviation over a period of time, like you can take 12 months average, or you can take 5 days average. Okay, so weekly rolling average or yearly rolling average, whatever you want, but you can take it and plot it, and you can check whether these both the graphs are collinear to the line of time, or the it's like a line touching the zero for every value of t. Okay, so it's constant over t. Okay, next thing is like you have some statistical model, like the hypothesis testing. Okay, what is the null hypothesis testing? That means you assume your data is not stationary. Okay, and then you have a significance level. Let's say the significance level is 0.05. Okay, if your observations or the data collected actually support this null hypothesis, like a p-value is calculated, and that p-value, if it is less than 0.05, then what we will do, we will reject the null hypothesis and accept that the data is stationary. And if it is greater than the significance level, then we'll accept the null hypothesis and say that, okay, the data is not stationary. So that is the like augmented decay Fuller test. Okay, so there we'll do the null hypothesis testing to accept the data is stationary or not. Okay, so now in the next part, what I'll do, now your data is fit enough to apply any statistical model. Now we'll talk about the statistical model ARIMA. What is ARIMA? So it has three components. One is the auto-regressive components. Okay, so it's like your today's data is a yield of your yesterday data, or your day before yesterday data, or your like how much lag it is depend upon. Okay, it can be t-1, t-2, t-3, t-4. Okay, the last 4 days data is very significant in determining your today's data. Just like an example, like if it was raining in last 4 days, it's most probable that today also it will be raining. Okay, but it's like not so obvious, because like it may or may not, but probability is more. And in the summer, if there is no rain in last 4 days, then it's obvious that today is also not raining. And then the contrary, like if the last 4 days temperature is very high, it is more probable that today's temperature will be in the higher side. Okay, so this is, if this is like 4 or 5 or 6, that you need to determine. So that is the auto-regressive component of a time series data. Okay, and there could be a constant component. Okay, so like always there should be some constant. Like if it is summer, then always the temperature is like 20° extra. Okay, and then there is a variation. Okay, but this 20° part is like, I'm talking about India only. So this 20° part is like a constant portion of it. Then like day by day, the upper level vary. Okay, but this 20° become constant. Okay, in centigrade. Okay, and then the next part is the error. How much error is also contributing in determining today's temperature. Okay, so maybe yesterday temperature was wrong. How much wrong? Okay, so that also having a contribution in today. Okay, so then how many lags in this error component also taking part in our prediction. Okay, so there could be a like auto-regressive part, and there could be some error lag part. Okay, So there will be three orders to determine the ARIMA model prediction. One is the p-value. Okay, p-value is the auto-regressive lags. Okay, how much lag it is required to predict a today's data. So like there I will discuss about the like PACF or ACF testing, like autocorrelation function or the partial autocorrelation function. So these two things actually determine like when your like, so if the data is periodical, when the data actually reach zero, okay, by using that autocorrelation. Okay, and partial autocorrelation also same when it reaches zero. Okay, so that portion of time, okay, so if it is like 3 lags when it reaches zero, so that is more significant. Okay, so we'll see that how PACF and ACF will determine your p-value and q-value. Okay, q-value is the error part, the moving average part. Okay, so now let's see how these things actually work. So what could be your data transformation, okay, to achieve the stationarity and to get your p and q value. Okay, and to get the p and q value accurate, there is another order, you can say, is significant, that is the difference part, differentiation, order of differentiation part. Okay, so that is the d value. Okay, so if p and q value is not determined correctly, then you need to change your d value as well. That's why it's called ARIMA, autoregressive, integrated and moving average. Autoregressive is the p, integrated is the d, and moving average is the q. Okay, now like first is how you can decrease the variation of any like time series data over time, right? So you know, if I take the log of it, okay, all the data, okay, so if the data is x, so I will take log of x. Okay, so whatever the variation of it will decrease. Okay, so if the standard deviation is 6, then it will reduce to 1. If the mean is like this high, then it can be like this. Okay, so you can like decrease it to some extent by taking log of it. Okay, so that is one way to achieve it. There are some other way as well. Okay, and then you take the log of the data. Okay, so I said like you just get L out of this. Okay, and now it has two parts, right? One is the like L stationary part, and another is the L trend part, right? So if this is the data now, so it has two parts, like L stationary and L trend part. Okay, now if I get the moving average of it, this L data, okay, moving average means I'm getting that like weekly, like last 5 days mean. Okay, so then it is also varying in the same way, right? We just saw it. See, the moving average is varying with the original data. Okay, so the rolling mean, you can say. Okay, so this is like, you say you have the differentiation of like 1 day or 2 day or no day. Okay, so you just get the L and A as same, then D is equal to 0. If there is a differentiation of 2, like obviously I'll get like this. So A is equal to L, this is the time, okay, not this trend. Okay, so I just write it trend. Okay, this is LT minus LT minus 1. Okay, so this is the differentiation is 1. Okay, it can be LT minus 2, the differentiation is 2. Okay, so now this A is also having two parts, right? One is the A stationary and another is the A trend. Okay, so now if I subtract A from L, then what is the common part of it? Like that trend part. Then A tier and L tier is like almost same, right? Like if L is going in this way, A also by some extent go in this way also. So the trend part you can see the same. Okay. So if I subtract A from L, then I will remove the trend part. Okay. So now I have removed the stationarity and I have removed the noise and I have removed the trend as well. So this is the way you can do the data transformation. So now the differentiation is like 1. So you should be aware of the hyper differentiation. Okay, you should not take like a value like 15 or 16 like it can be either 0 or 1 or 2. Beyond that, it could be like hyper differentiation. Okay, so you just determine that your d value is 1. Okay, now you want to know what is your p value and what will be your q value. So then like we'll use the ACF and PACF. Okay, so we can plot the PACF and ACF like this. Okay, so I will see how you can do it using Python, but let's see that you can achieve these kind of two plots. Okay, now see, after 2 legs only it reach 0. So your p value is 2, and after 15 value it reaches 0. So your q value is equal to 15. So that is very high. So you need to do sine camera stationarity, like differentiation you need to change. Okay, so if your p value and q value is very high, then what you need to do, you need to change your difference d value. Okay, so let's see what all cases you can get what all value. Okay, so there is a matrix you can say. So if ACF taps to 0 in some fashion and PACF is non-zero value at first p points, then that will be your p value. Okay, and then if ACF is having non-zero values at first q point and 0 values after that, okay, then that will be your q value. But if those two plots is never reaching 0 at some point, then like it's a non-stationary series. You need to change or transform your data. Okay, the next part is like there is no correlation. Okay, the graph is not moving anywhere, so that is a random graph. Okay, so you cannot achieve stationarity in that because there is no relation between those all data points. Okay, so that is the way you can get your p, d and q value and how d is contributing to p and q. Okay, we will do in the next section a COVID-19 data. I have received this data from Kaggle, and this data I have used for this ARIMA model, and we will do the future forecasting for some months, like how could be the COVID cases. Okay, thank you so much for attending this session. So we will do the coding part in the next session. Please stay tuned. Thank you so much.